Well, hi, everybody. The purpose of this video is simply to practice the basic stuff about number theory that we've learned in the very first part of this course. Things about divisibility, greatest common divisors, and things of that nature. How to write the greatest common divisor as an integer combination of the two numbers, those sorts of things. So this is simply a practice session. I encourage you to pause the video as we go through this and try these problems for yourself first. After you've had a chance to do that, you can certainly hit the play button and watch me as I talk through them and just kind of line up your solutions with mine and see how things stack up. Okay, so just a little encouragement. We're not doing any new material here. This is simply a chance to practice what we have done up until this point. So there's going to be three examples, and the first one I actually wrote on my board already. If we take three integers, A, B, and C, and let's denote the greatest common divisor of A and B with D1, and the greatest common divisor of A and C with D2. If A divides BC, let's prove that A would have to divide D1, D2. Okay. Now, there might be some things that we can write down right off the bat. If you want to pause this video and try to write them down for yourself first, that would be great, because I'm going to step up to my board here in a moment and start working this out, just using the basic information that we've learned up until this point. Okay, well, for the solution, I'm just going to try to translate what's on my board up to this point. I'm assuming that A divides C. So let's see, what does that allow me to do? Right? It means that there is some multiple. I'm going to just use an R for this, but of course you can use whatever letter you like. But there is some multiple of A that is equal to BC. So there exists an integer R with BC equal to AR. Presumably, we're going to use that at some point. Now, likewise, we also have D1 and D2. These are the greatest common divisors of A and B and A and C. So we can actually write both D1 and D2 as integer combinations of the respective letters of A, B, and C. So what I'm going to do is I'm going to find, let me use some, let's say X1 and Y1 in the integers such that D1 is AX1 plus BY1. Okay, and then similarly, I would also like to find X2 and Y2. So this is really a very important idea, that the greatest common divisor of two numbers can be written as an integer combination of those two numbers. We've been using that a lot so far in the material. So in this case, D2 could be written as AX2 plus CY2. This is really just writing down everything that we know so far. Now, what I'd like to do is now figure out how to prove that D1, D2 is a multiple of A. Well, if we just simply look at it, if we look at D1, D2, we can obviously just replace what we have, AX1 plus BY1 times AX2 plus BY2. We can replace that in the expression for D1 times D2. And we just need to show that this is a multiple of A. Well, you can see that if you were to multiply this out, most of the terms are going to have factors of A in them. For example, when I FOIL this out, I have A squared X1, X2. I have AB X1, Y2. I have BA Y1, X2. And finally, I have B squared. Oh, you know what? I made a mistake here, didn't I? This should be CY2. I'm so sorry. That should be a CY2. Otherwise, this really isn't going to work. So I have I need to make sure I haven't made a mistake here. This should have actually been AC x1, y2. I'm so sorry. And the last term is BC y1, y2. Okay. If you need to pause and make sure I did that right, I just had a little typo on the D2 expression there. So I've FOILed it out, hopefully correctly now. And I see a factor of A here and here and here. There's no A explicitly written over here, but I do have this, don't I? BC is actually A times R. So if I wanted, I could come up, I'm going to just come up here to the top here and continue. This is simply going to be A squared x1, x2 plus AC x1, y2 plus BA x2, y1. And then, as I said, BC can be replaced by AR y1, y2. And now all four terms have factors of A in them. Okay, I'll let you guys copy the rest of this down. I won't rewrite the whole thing in there, but the point will be that now A therefore divides D1, D2. A divides D1, D2, which is what I was trying to prove on this example. A basic little problem involving writing the GCD of two numbers as an integer combination of those numbers and using the definition of divisibility. It's not too hard, it's not too easy. It's a nice example to kind of put some things together. I'll let you pause if you need to. Think about the solution. Make sure that this is something you feel like you could do if you had to. And then once we're done with that, we'll go on and try another example. Okay, let's move on. I will come back up here and write down another problem. Again, this is just practice with the things that we've looked at so far. It's nothing in terms of new material by any means. So for number 2, another chance to practice some things here. What I'm going to do is I'm going to assume that A and B are relatively prime. In other words, I'll just write it here. The greatest common divisor of A and B, let's assume that that is equal to 1. And what I would like to do is prove that the greatest common divisor of A times C with B is actually equal to the greatest common divisor of C with B. In other words, this factor of A here doesn't do anything to change the greatest common divisor of anything. And that's because, I don't know if you can see that. Let me write it down here. So what I'm going to do, let me try this one more time. Sorry. I would like to prove that the GCD of AC with B, right, is equal to the GCD of C with B. Okay. Now, when I was talking about the Euclidean algorithm, we actually proved a fact that one GCD was equal to another. When you're proving that two GCDs are the same, a really good strategy is to prove that all of the common divisors of, the first two numbers agree with all of the common divisors of the other two numbers. This is kind of the idea here. So let's try and take advantage of that. Okay. So what I'm going to do for the solution here, grab a marker here. So for the solution, I'm going to define a couple of sets. I'm going to let S, right? I'm going to let S be the set of common divisors of AC and B. And then I'm going to let T be the set of common divisors of C and B, right? And if I can show that these two sets are the same, then the greatest element of S is going to be the same as the greatest element of T. If the two sets are the same, then their greatest elements are the same, which is actually what we're proving. So I really just need to show, I just need to prove, and I'm going to claim here, that S is equal to T. This is the claim. So I'm going to have to prove that these sets are subsets in both directions. This is kind of a standard way to do this. I'm going to start with the backwards subset relationship because it actually happens to be a little bit easier. I know that ahead of time, but ultimately it doesn't really matter. I'm going to imagine that I've picked an element, I'll call it X, that belongs to T. This means, of course, that X is a divisor of both C and B. So X divides C and X divides B. Well, if X divides C and X divides B, I would like to show that X also divides AC. Well, the thing is that we can write C as X times R for some integer R. And so now, of course, I can multiply through by A. This is kind of the trick that you would want to use here. I'll put the A over here with the R. So just multiplying through by A on that equation, right? This implies now that X divides AC. So X is going to divide AC, and it's also already dividing B. And so X is an element of S. That much we already know. So T is a subset of S. Have so far. If it's too fast, just pause the video, give it a moment to think it through. I don't want you writing so frantically that you don't have a chance to think about this. Remember, the goal is after we're done with these problems, you should feel like you could go back and just do them without my help, right? That you could do them kind of on your own. Just a good way to sort of assess how you're coming along with all of this. Let's try and go the other direction now. Let's pick an element, I'll call it X again, that's in S. And I would like to prove that it is in T. Now, the fact that it's in X means that X divides AC and X divides B. Now you notice, by the way, I haven't really used the fact that the greatest common divisor of A and B is equal to 1, right? But we're going to use that now in this backwards part of the proof. Notice that X divides B. So all of the parts of X are inside of B. So none of them can be part of A whatsoever, right? This actually implies that since the GCD of A and B is equal to 1, right? We can say that the GCD of X with A is equal to 1. X, see, if X has any common factors with A, right, then X could not have any common factors with B, because if there's common factors of X with both B and with A, then the GCD of A and B would not be 1. So we have to have the greatest common divisor of X with A is 1. However, we know that X divides AC. So now I want you to think about this. There's a result from our work so far that will allow us to draw a conclusion from this. Basically, from this fact, if X divides a product of two numbers, but has nothing in common with one of those numbers. No common factors with A, but yet X manages to divide A times C. If you need to, pause the video, look at your notes if you need to, if you're not thinking what I'm thinking of, until you realize we have this written down as one of our results. It's actually a named result. And that named result is, are you ready? It is the Euclid's lemma. By Euclid's lemma, right, we can actually say X divides C. X has to divide C in this case. And that means that X is a common divisor of both B and C, and so it lives in T. S and T are therefore equal. And that actually proves that the GCDs are equal. Exactly. Okay, so this backwards part was a little trickier. We had to actually use Euclid's lemma, and it's really only for this part where we use the relatively prime assumption on the A and the B. Okay, great. I hope it's making sense so far. I'm going to do one more example. Back up, we'll practice one more problem here, and then we'll call it good. Nice thing about video, you can always rewind stuff if you've missed anything. But let's do one last example. I'll call this number 3. And this just says, again, let's assume that A and B are relatively prime. Okay. And then what I would like to do is prove that the GCD of A plus B and A minus B is at most 2 of all things. It is at most 2. Okay, hopefully this is legible. This just says at most 2 right here. All right. So here's the way I'm going to do this one. I want to show that the only possible common divisors of A plus B and A minus B, the only thing it could be is either a 1 or a 2. Let's suppose we have a divisor. Suppose that D, let's suppose we have a common divisor, I'll call it D, and that D divides both of these numbers, A plus B and A minus B. I'd like to show that D is at most 2. This is the claim. Well, remember, guys, that when D divides 2 numbers, it's also going to divide any combination of those 2 numbers, right? We can actually add these together. I actually just want to add them for a moment. A plus B plus A minus B. And in other words, D is going to divide 2A. All right. And similarly, D would also have to divide the difference of those 2 numbers. And if you just subtract them, you actually get 2B. So D is actually a common divisor of 2A and 2B. And so it would have to be less than or equal to the greatest common divisor of 2A and 2B, right? But if I have the greatest common divisor of A and B, there's no common factors between A and B, and I just double both of the numbers, what I'm actually going to do is I'm just simply going to double the GCD, right? So we could actually just write it like this. And we get the conclusion almost immediately now. If A and B are relatively prime, then 2A and 2B have only one common divisor greater than 1, which is 2 itself. And so we've convinced our claim, hopefully it's convincing. D is less than or equal to 2. So these are 3 fairly short little practice problems to use the definitions of divisibility, remind ourselves what greatest common divisors are all about. This is, of course, fairly theoretical work. We're using Euclid's lemma. We're using the theorem that the GCD of 2 numbers is an integer combination of those 2 numbers. We've seen all of those sort of highlight results from the beginning part of this course being used in some of this practice. So I encourage you to maybe try the problems again without listening to me talk through it. See if you can yourself produce these. And certainly as we go into the weeks and months ahead, coming back and trying these again, make sure that the ideas are still there, would certainly be a good idea. I hope it's been helpful. I hope you've enjoyed practicing these problems with me. If you've got any questions on it, be sure to let me know. In the meantime, I hope you guys have a wonderful rest of your day. Thanks for being here, and we'll talk again soon. Bye for now.